Hi there, Mrs. Lindsay here to review with you the properties of real numbers. Real numbers, you may ask, what is a real number? Or aren't all numbers real? Well, let's get into it and we'll see. The real numbers are composed of different subsets. You can think of them as mini families within a family. So when you first learned as a young child how to count, you probably started with the number 1. And you continue to count 1, 2, 3, 4, 5, and so on. Eventually, your parents got annoyed and told you to stop, but you soon realized that you could count forever, infinitely, in the positive direction, starting with the number 1. We call those natural numbers or counting numbers. Soon, maybe one day when you had nothing, you realized that there was a number called 0. If we join 0 with the natural numbers, we have the whole numbers. You can think of whole numbers, the O in whole numbers might remind you of 0. So the natural numbers joined with 0 are called whole numbers. Remember, there are no fractions. We can count them. In school, sometime you learned about integers, which means you could count in the negative direction. We call those integers. So now we know that you can count forwards and backwards infinitely. There are positive natural numbers, negative natural numbers, and between them is 0, and we call these integers. These are discrete numbers, which means you can count them or list them. Yes, they're infinite, they go on forever, but you can still list them and continue to count, assuming no one stops you. Now, natural numbers, 1, 2, 3, etc., are all whole numbers. They're all contained in the set of whole numbers. So, look, here they are. But all whole numbers are not natural numbers because we have 0. The same is true. Whole numbers are all contained in the set of integers. 0, 1, 2, 3. Here they are. They're all integers. However, all integers are not whole numbers because we have the negatives. So negative integers are not whole numbers. Not all integers are whole numbers. All whole numbers are integers. So it kind of flows up, but not down. Now, there are many other numbers between the integers. So between 0 and 1, we have, for example, 1/2. And between 0 and 1/2, we have 1/4. Between 1/4 and 0, we have 1/8, and so on. It's very dense between 0 and 1. There are infinite numbers between 0 and 1. We call these rational numbers. And yes, they do look like fractions. Both the numerator and denominator of the fraction have to be integers, and the denominator cannot equal 0. Remember, if the denominator is 0, if you divide by 0, this is non-real. So here's one example of a non-real number. Dividing by 0. The denominator being 0 makes it not real. We're only going to deal with real numbers. So we will never divide by 0. Now, rational numbers can be negative or positive. So I can also make these fractions between 0 and 1. I can make them between 0 and -1. So I can have -1/2 or -1/4. and so on. If I write these as decimals, they would be either terminating, which means ending, for example, 0.25, or they would be repeating, for example, 0.3, which also happens to be 0.3 repeating. We'll put a nice clear bar over that. 0.3 repeating, which happens to be 1/3. I could repeat 2 digits, like 0.14. If I put a bar over the 1 and the 4, that would be 0.14, 14, 14. It would continue to repeat. So anything that I can put a bar over, a repeating decimal that I can put a bar over, never ends, can be written as a fraction. It is rational. So there are some numbers that are not rational. So real numbers that are not rational are called irrational, and they cannot be written as fractions. A very famous one that we all know is pi. If you type pi into your calculator, you get a non-repeating and non-terminating decimal. But there are many other irrational numbers besides pi. Any positive number that's not a perfect square, if we try to take its square root, will be irrational. So for example, square root of 7, square root of 35. If we type these positive, non-perfect square roots into our calculator, we will get a non-terminating, non-repeating decimal. Here's a non-terminating, non-repeating decimal. 0.15, 115, 1115, ... Okay, the 3 dots means it's going on forever. And we think we see a pattern here. We have a 1 and a 5, and then 2 1s and a 5, and 3 1s and a 5. But there's nothing that we could put a bar over. There's no repeating pattern here. There is a pattern, but it's not a repeating pattern. This would be an irrational number. Remember, rational numbers and irrational numbers are not discrete. They cannot be counted. They cannot be listed. They're what's called continuous. So, just to review a little bit. Some numbers belong to more than one number set, right? So for example, let's look at -10. -10 is clearly an integer, but it's not a whole number. It's not positive. It is rational because I can write -10 as a fraction. -10 over 1 would work. But it's not irrational. Rational numbers are not irrational. Irrational numbers are not rational. They're separate. Let's look at 8/5. 8/5 is a fraction. Clearly it's rational. But it's not an integer because it's not countable. It's not irrational because rational numbers are never rational. Rational numbers are never irrational. Let's look at 10. 10 is a natural number. It's countable. It also makes it a whole number. It's also an integer. And it's also rational. You can write it as a fraction, 10 over 1. 0 is not a natural number, but it is a whole number. It's also an integer. It's also rational. 0 over 1, we can write it as a fraction, but it is not irrational. Okay, let's jump over here to pi. Pi, we all know that that's an irrational number. Irrational numbers, never rational. Okay, let's look at this one. 13.12, 122, 1222. Well, that's kind of got a pattern, and it's certainly non-terminating, but there's no repeating pattern because we always have an extra 2 every time. So that's going to be irrational. So that's 13.121221222 ... That goes into irrational. And this last one, negative 7.828282, well, that's rational. It's got a repeating pattern. And I'll even write that with a bar in bar notation. 7.82. Put the bar over the 82, meaning it repeats forever, the 8 and the 2. Okay. So these sets of real numbers have properties that pertain to all of them. The first property, and one you might remember from last year, is the commutative property. There's a commutative property of addition and multiplication. The commutative property means the order changes. If I change places A plus B, if I change the order and make it B plus A, that's the commutative property of addition. And similarly with multiplication, AB or BA. The associative property. Remember, if the order is the same, then it's not the commutative property. So check the order before you look at anything else, right? If you're trying to identify a property, look at the order first. In this case, the order is the same. A, B, C, A, B, C. The order is the same. The thing that's changing are the parentheses or the grouping symbols. So A plus B is going to be added first. And in this case, B plus C is going to be added first. So the order or the emphasis changes for the associative property. All right? So remember, this property, A plus B plus C, is still going to come out to A plus B plus C, no matter which addend you do first. The same with multiplication. No matter which factors you multiply first, it's all multiplication and the order is the same, the associative property means that you're going to have equivalence. So those two properties have multiplication and addition. The identity property results back to the original. So the additive identity is 0. If you add 0, you get the original or the identical number back again. So A plus 0 results back in A. Multiplying by 0 isn't going to give you the original number back again, but certainly if you multiply by 1, you'll get the original number back again. A times 1 results in A. Now, some people confuse the inverse property and the identity property. The inverse property results in the identity. So for the additive inverse, you're going to get it to equal 0. You're going to kind of undo the problem. So here we have the opposite. I'll rewrite this for you because you can't see it. A plus negative A gives you 0. If we want to undo the A by adding, we add the opposite. Additive inverse is the opposite. The multiplicative inverse is the reciprocal. Again, we want this to equal 1, which is the multiplicative identity. So we multiply the reciprocal. A times its reciprocal, A times 1 over A, gives you 1. Sorry, that should be a 1. Okay? A times 1 over A gives you 1. Or if it's a fraction, A over B times its reciprocal, B over A, results in 1. The distributive property over addition means that you're going to make a copy of this number that you're multiplying to some type of polynomial expression, and you're going to multiply this number to each term in the expression. So you're going to multiply a to the b, and you're going to multiply, this should say a to the c. And you're going to do the same thing over subtraction. The distributive property holds over addition and subtraction. A times b, and then minus, again, sorry, this should say a times c. And the last property, the multiplicative property of 0, when you multiply by 0, you will annihilate or destroy your entire expression. Anything multiplied by 0 destroys it and makes it 0, no matter what it is. So a times 0 equals 0, but you can have anything. A, b times x plus c plus 17. If you multiply that by 0, what do we get? Destroyed. 0. And those are your properties. You're going to have some practice tomorrow in class. And if you have any questions, you can ask your teacher in class tomorrow, and we'll be happy to straighten it out for you. See you then. Good luck.